getting involved in databases back in the 80s when I was asked to port Ingress to IX 6.5. At that point, the best recommendation for how do you set up a database is to set them up directly on the raw partitions. Put your log file on a separate disk and only use the outer segments where it's fastest. And stripe all the rest of your table space across as many spindles as you can find to try and get speed. And don't let any of the operating systems, buffer cache, or file systems to get in the way between your database engine and your disks. So that was the recommendation. But let's look at a typical storage stack today. It looks something like this. This is simplified. At the bottom, you've got your disks. And disks do all sorts of weird and wonderful things inside. And they remap your requests, so you don't know whether, if you take this block and then that block, whether they're actually going to be contiguous on the disk or not. You don't even know whether it's going to be the same unit, because an SSD could have lots of different flash cards and it stripes things internally, it's made internally. You've got no idea of the topology inside your disk. On top of that, we put a RAID controller. That may or may not export the topology of the underlying system to the next layer up. And then if you're a systems administrator for an enterprise class machine, you're probably using a logical volume manager on top of that, which again hides the topology of the things. It creates volumes that may or may not be striped over multiple RAID arrays, may or may not have caches involved with an SSD in there somewhere. And then you've got the page cache or the buffer pool, which I put in as a layer, but isn't really, it's sort of off to the side. And then you've got your file systems on top of that, and a VFS on top of that, and then a system call layer, and you put your database management right at the top, and it doesn't know what the topology is anymore. So the user space doesn't understand the disk layout, and it can't optimize for it. That could be a good thing. I mean, maybe the kernel knows better than the user space how to optimize stuff. But database management, I don't know. And file systems also can't see the disk layout, and XFS in particular really wants to know how the disks are divided up so it can optimize parallelism at the lowest level. So let's try turning it upside down. Let's put a relational database management system right at the bottom, directly on the disks, which is as close as we can get to the hardware. Put Fuse or something on the top because database managers want to talk to user space, they don't want to talk to kernel. And Fuse lets you put a file system in user space. And then we can have all those other things on top, and let's see what's going on. I wanted to do that for ages. If you think about what a file system actually is, it's a set of mappings. It's a mapping from a name to a set of metadata, all the ownership and file modes and all that stuff that you do when you do an LSHL. And it's a mapping from name to file content. In POSIX-related systems, we don't have any funky file systems that do index sequential access method or anything like that. That's assumed to be done at user space. The other place that you've got a mapping is from name to name for symbolic links, so a symbolic link is just a mapping from name to name. When we've got this in the file system, we want to order the writes for consistency. So you want to make sure that you do things in the right order, so if you get a crash, your file system can still be understood. Your disk layout can still be understood by the file system when it comes up again. We want to make sure that writes to different files are isolated from each other. So that if I write to this file, it doesn't interfere with the writes to this file. And if possible, your file system should even make the performance not noticeable. So if you've got heavy writes on this file, it shouldn't really affect the speed of writes in this other file. And a good file system will spread things across the spindles it's got, so you do actually get some of that isolation. And the other thing you really want from a file system is if you call fsync or an open file, when that fsync returns, you know that if there's a crash, the data is actually on permanent storage, you can get it back. I've had some file system implementations that's not true. It's a bit annoying. Now, if you think about this, this is exactly the standard ACID properties that the database has got. With the addition of atomicity, some file system operations have to be atomic. Creating a link, doing a rename, you expect those to be atomic. And there's a few others too. But the other ones, the ones we just talked about, they're just the ACID things. So let's use a relational database management system that handles replication, perhaps, at the bottom level. This makes it really easy to add new attributes. So maybe we want to use an Apple-like file system with a resource fork, or maybe we want to try funky ACL mechanisms. And you can do that very easily. And because the database engine guarantees consistency, maybe we can throw away the need for FSCK ever. And if we use a relational database system that handles replication, for example, MariaDB with Galera, then we can get distribution for all those free. But, there's a big but here. Most of the modern relational database management systems we've got, such as Postgres, rely on aspects of the file system for their operation. They don't run on raw disks anymore. At least Postgres does. I discovered only last night by talking to one of the MySQL maintainers, who happens to be at the conference, that MySQL you can actually configure to do on raw disks. But because I only found that out last night, I haven't tried it yet. Anyway, I've been looking to do this for ages but haven't had time. One of the things our group does, we have a research group at the university, is every year we invite good students to come and spend the summer months with us embedded in the research group. And this year, Sam Lee turned up and he wanted to do this task. So he started looking at what it would take to put a relational database level, what table schemas you'd need, what queries you'd need to be able to do the stuff. But while he was doing preliminary work, he discovered that it's already been done. This sounded like it was going to be a really short project. Mr. Tsukasa Hamano from Japan and Mikhail Ludwig, who's from somewhere up north but currently lives in Southeast Asia, created a thing called MySQLFS back in the early 2000s. It hasn't been touched since 2009, which means it doesn't compile with GCC version 8 anymore. That was fairly easy to fix. What it looks like is this. This is the schema. You've got three tables. The tree table, which maps inode to parent inode to name. So it's indexed on name, and it's indexed on inode. So you can do a search on the inode to find the name, and you can do a search on the name to find the inode. That already gives you something that's better than most file systems, because you can't actually look up a name from an inode very easily. And by joining on inode to parent, you can get everything that's in a directory. You've got the inodes table, which contains all the metadata, except for the number of links that a file has. That gives you the modified time, the creation time, the mode, and two extra things, whether the inode's in use at the moment, and whether it's been deleted. Because this file system doesn't track n-links, you need to have a separate flag to say that it's been deleted. You can't
Summoner's Rift. "30 seconds until minions spawn." Minions have spawned. First blood. An enemy has been slain.